Hi, my name is Marty Burke. I'm a professor of chemistry at the University of Illinois and the Howard Hughes Medical Institute. And I'm very excited to have this opportunity to tell you about a recent discovery in my lab that we're hopeful is going to have a big impact on our ability to discover new medicines. So when I was a medical student, I became absolutely fascinated by a class of compounds called small molecules, which turn out to make great medicines. They're very small, but also very complex little structures that have a tremendous amount of information packed within their framework. Turns out if you have a disease that's caused by too much function, that is the proteins in your cells, if one of them is hyperactive, small molecules are really good at binding to those proteins and turning them off. And this can be a very powerful way to treat disease. We also became very excited about the possibility that maybe even when you're missing a function, might it be possible to find small molecules that could actually replicate the function of those missing proteins, in a sense operating like a prosthesis on the molecular scale? With those goals in mind, we became really excited about a specific small molecule called amphotericin. This is a naturally occurring small molecule. It is a very complex structure, densely packed with information, and already is known to perform a very important protein-like function, and that is that it can form ion channels in living cells. And at this point, we ran into a major bottleneck because it turns out making complex small molecules like amphotericin in the laboratory is a really difficult problem. So we became very excited about an idea. And the idea was if we could put all the information that we need up front into a collection of building blocks and then just use one simple process to stitch those building blocks together, could this in fact allow us to make molecules like amphotericin and many other small molecules in a much more efficient and flexible fashion? So you can think about a building block like this one, where interestingly it has a lot of really good information already pre-installed, right? Obviously it's small, it's shaped like a square, and it's got the color blue. We can take other building blocks in which other information has been, again, kind of pre-installed, and they all have this kind of two-sided nature that allows us to use the same kind of simple coupling process to bring them together. We can then do this in a very controlled and defined way, and therefore make very interesting structures using the same kind of simple iterative building block coupling approach. So this allowed us actually to make a very important derivative of amphotericin. We then went on to ask, how many building blocks would it take to make the thousands of other naturally occurring molecules like amphotericin that are found in nature? And the result that we've recently discovered is very exciting. It turns out with just 12 different building blocks, you can make thousands of different natural product-like structures in a very efficient and very flexible way, with the same basic concept of pre-installing the information within the building blocks and then mixing and matching them in all different combinations. Excitingly, actually, many of these building blocks are now available in catalogs, so other people can simply buy them and use them in their own research labs. This is having a very powerful accelerating impact on the way in which these small molecules can actually be accessed. But we're increasingly convinced that ultimately we could have a simple set of building blocks that we could put in a bucket, hand over to either non-chemists throughout the world, and allow the functional potential that these molecules possess to be accessed in a much more efficient and flexible manner, and thereby have a big impact on the discovery of medicines.